Imagine standing on a silent, airless world where cosmic myths suggest giant glass domes shimmer under the unfiltered light of the sun. What if everything you've ever heard about artificial lunar architecture, secret ISS feed cuts, or nuclear detonations on the moon was nothing more than optical illusions and Cold War misdirections? Today, we explore the quiet calm of our local space environment, untangle the physical mechanics of solar eruptions, and look at how artificial intelligence is offering us an unprecedented early warning system for space hazards. You're listening to the Daily Space Podcast by Flarient, your daily conversation about space weather, solar activity, and cosmic events. I'm Ollie, and today is Tuesday, August 25th. Let's get into what the sun is doing today. If you're looking for dramatic solar tempestuousness today, I'm afraid the sun has decided to give us a bit of a breather. Looking at the live telemetry coming in from NOAA's Space Weather Prediction Center and the GFZ German Research Center for Geosciences, the space environment surrounding Earth is remarkably tranquil. Right now, the planetary KP index, which measures global geomagnetic activity on a scale from 0 to 9, is hovering at a tiny 0.33. Over the past 24 hours, the maximum value recorded was just 1.67. What does that actually mean for us down here on the ground? Well, anything below a KP of 2 indicates completely unsettled to quiet conditions. The geomagnetic field isn't experiencing any notable buffering or compression from solar structures. Our magnetosphere is sitting comfortably in its baseline state. Taking a look at the solar wind parameters, the speed is lounging around a modest 364.5 kilometers per second, paired with a particle density of roughly 2.9 protons per cubic centimeter. When you combine low speed with low particle density, there is simply very little kinetic energy being transferred to Earth's magnetic envelope. Furthermore, the interplanetary magnetic field's vertical orientation, what we call the BZ component, is reading around positive 2.6 nanotesla. Remember, for high-latitude geomagnetic activity to ramp up, we usually want to see a strongly negative BZ component, which allows the solar wind's magnetic lines to interconnect with Earth's northward magnetic field. Because BZ is pointing north, those doors remain firmly closed. Looking at our DST index, the disturbance storm time index that monitors the strength of the equatorial ring current, it sits around -10 to -31 nanotesla, showing no major storm time ring current buildup. What about the auroras, you ask? Well, with the auroral oval power index peaking around 18%, sky watchers at mid to high latitudes will likely have a quiet night. Unless you are situated right up near the Arctic Circle, visual aurora displays are unlikely tonight. But quiet periods like this are ideal for space hardware testing and routine satellite calibration. Moving from current conditions into our featured articles today, we have a fascinating mix of industrial space concepts, core plasma physics, and orbital infrastructure resilience. Let's start with a topic that has quietly shifted from speculative science fiction into boardrooms: asteroid mining. Our latest piece on Flarient explores how harvesting near-Earth asteroids could become a tangible economic reality in the coming decades. You see, metallic asteroids are essentially leftover building blocks from the early accretion phase of our solar system, packed with iron, nickel, cobalt, and platinum group metals. A single kilometer-wide platinum-rich asteroid could contain more refined platinum group metals than have ever been mined in human history. But beyond precious metals, the real killer application for early space mining isn't bringing gold back to Earth, it's water ice. Water in space can be split via electrolysis into liquid hydrogen and liquid oxygen, rocket fuel. If we can harvest water directly from volatile-rich carbonaceous asteroids in orbit, we eliminate the immense energetic cost of lifting thousands of tons of propellant out of Earth's deep gravity well. It completely changes the economics of deep space exploration. Next up, we have an important educational article addressing a common point of confusion: the physical distinction between solar flares and coronal mass ejections, or CMEs. People often use these terms interchangeably, but they are fundamentally different physical phenomena. A solar flare is an intense flash of electromagnetic radiation triggered by magnetic reconnect ion in the solar atmosphere. Because flares consist of light across X-ray, ultraviolet, and radio wavelengths, they travel at the speed of light, reaching Earth in just over 8 minutes. They instantaneously ionize the upper atmosphere, causing high-frequency radio blackouts on the daylight side of Earth. A coronal mass ejection, on the other hand, is a physical cloud of billions of tons of solar plasma and embedded magnetic fields violently launched into interplanetary space. CMEs don't travel at light speed, they travel at velocities between 300 and 3,000 kilometers per second, taking anywhere from 15 hours to several days to arrive. When a CME strikes Earth's magnetic field, it triggers geomagnetic storms, inducing electrical currents in power grids and lighting up the auroral oval. So, while flares are light-speed electromagnetic flashes, CMEs are massive physical plasma clouds arriving days later. Understanding that difference is crucial for space weather forecasting. Our third article examines solar radiation storms and their specific impact on high-altitude operations and space assets. Radiation storms happen when energetic protons are accelerated by powerful flares or shockwaves ahead of fast CMEs to near-relativistic speeds. These energetic protons arrive in minutes to hours and funnel along Earth's magnetic field lines toward the polar regions. When they hit the ionosphere, they cause polar cap absorption events, blocking high-frequency communications for commercial airlines flying transpolar routes. Moreover, these protons can penetrate satellite shielding, causing single-event upsets or bit flips in flight computers. Which leads naturally into our fourth article, how satellite engineers actually design spacecraft to maintain communication during geomagnetic storms. When high-energy plasma engulfs a satellite, differential charging can build up across static surfaces, risking destructive electrostatic discharge. Engineers combat this using conductive surface coatings, Faraday shielding around sensitive electronics, and redundant hardware architectures. When a severe storm hits, operators can put non-essential systems into safe mode, align solar arrays to reduce atmospheric drag in low Earth orbit, and use error-correcting codes in data transmissions to recover corrupted signals. Turning now to current space events and sky-watching targets, today we are following the close approach of near-Earth asteroid 2022 UP6. This celestial visitor is passing safely by Earth while our space weather background remains exceptionally calm. What makes flybys like 2022 UP6 so useful for astronomers is that quiet solar wind conditions provide a pristine background signal. Radar observations and light curve tracking can measure the physical shape, rotation rate, and surface reflectivity of the asteroid without high solar activity interfering with sensitive ground telemetry. If you are stepping outside to look at the night sky this week, keep your eyes on the western horizon right after sunset. Venus has recently reached its greatest elongation east, placing it high above the horizon in twilight. It shines brilliantly as the evening star and offers a fantastic target for binoculars or small telescopes. Meanwhile, back on the solar forecasting front, solar physicists have unveiled promising results from new artificial intelligence models designed to spot subtle magnetic precursors hours before solar flares erupt. Historically, predicting flares relied on manual classification of active region sunspots, such as the Mount Wilson magnetic classification. But machine learning algorithms trained on tens of thousands of vector magnetogram images from NASA's Solar Dynamics Observatory can now evaluate tiny shear stresses and magnetic flux emergence patterns that human analysts might miss. These AI diagnostics aim to extend our lead time for space weather warnings from minutes to several hours, giving satellite operators and power grid controllers vital time to implement protective measures before a flare or radiation storm strikes. Now, let's step into our fact-check section, where we examine persistent myths, internet rumors, and conspiracy theories about space science, evaluating them against empirical evidence. First up is a widespread social media claim that NASA deliberately cuts the live International Space Station video feed whenever an unidentified flying object or unexplained anomaly appears on camera. Verdict: false. This claim relies on a misunderstanding of how the ISS transmits video back to Earth. The ISS relies on the Tracking and Data Relay Satellite System, TDRSS, a constellation of geosynchronous communication satellites. As the station orbits Earth at 28,000 km per hour, it regularly passes between the coverage arcs of different TDRSS satellites. During these brief handoffs, or when ground station antennas repoint, the signal drops out, displaying a standard blue screen or loss of signal graphic. Furthermore, official independent reports, such as NASA's 2023 UAP Independent Study Team report, have repeatedly pushed for open data and higher resolution tracking, which directly contradicts the idea of an intentional suppression scheme. Our second claim suggests that the Cydonia region on Mars contains artificial pyramids aligned identically to the pyramids of Giza on Earth. Verdict: false. This rumor stems from low-resolution images captured by the Viking 1 orbiter in 1976, where grainy lighting caused natural landforms to resemble faces and structures. However, high-resolution imagery captured by NASA's Mars Global Surveyor and the High-Resolution Imaging Science Experiment on the Mars Reconnaissance Orbiter revealed these features to be standard geological mesas and severely eroded naturally occurring rock structures. The apparent symmetry was simply pareidolia, our brain's tendency to recognize familiar patterns in random shapes. Comprehensive spatial analysis has confirmed there is no geometric alignment between these Martian landforms and the pyramids of Giza. Our third claim states that nuclear-powered nations have secretly conducted nuclear bomb tests on the surface of the Moon. Verdict: false. No nuclear weapon has ever been detonated on or near the Moon. During the height of the Cold War in 1958, the United States Air Force did consider a classified study called Project A-119, which explored the feasibility of a lunar nuclear detonation as a demonstration of technical capability. However, the proposal was quickly abandoned due to launch safety risks, potential radio contamination of the lunar surface, and severe public backlash. People sometimes confuse this study with NASA's 2009 ICROSS mission, where an uncrewed Centaur rocket stage deliberately impacted a permanently shadowed crater at the lunar south pole. That was a purely kinetic impact, completely non-nuclear, designed to kick up a plume of dust so scientists could confirm the presence of water ice. Our fourth claim is a simple one, that the Moon has no gravitational field whatsoever. Verdict: false. Every object that possesses mass generates gravity, as governed by Newton's law of universal gravitation and Einstein's general relativity. The Moon has a mass of about 7.34 times 10 to the 22nd power kilograms, giving it a surface gravity of approximately 1.62 meters per second squared, about 1/6 of Earth's surface gravity. Not only did Apollo astronauts experience this gravity directly while walking on the surface, but NASA's Grail mission mapped subtle variations in lunar gravity caused by dense underground structures called mascons. In fact, the Moon's gravity is the primary force driving ocean tides on Earth every single day. Our final fact check addresses the assertion that giant glass domes, towers, and ancient alien cities exist on the Moon and are routinely airbrushed out of official NASA photographs. Verdict: false. These claims rely on distorted visual artifacts found in older archival film negatives, such as internal lens reflections, cosmic ray strikes on film emulsion, or long shadows cast by irregular crater rims. NASA's photographic archives are open to the public, offering uncompressed high-resolution digital scans from the Lunar Reconnaissance Orbiter that show the surface down to sub-meter resolution without any evidence of artificial construction. Let's summarize everything in today's daily brief. Today presents a peaceful intersection of observational astronomy and technological progress. While near-Earth asteroid 2022 UP6 glides safely past our planet, the solar background remains exceptionally quiet. With a KP index sitting below 1 and solar wind speeds around 364 km per second, Earth's magnetosphere is enjoying a period of minimal stress. These quiet periods provide critical windows for operational testing. As scientists integrate advanced AI diagnostic tools into solar monitoring systems, our ability to anticipate future flare eruptions and coronal mass ejections continues to mature rapidly. Whether we are tracking asteroid trajectories, debunking long-standing lunar myths, or preparing orbital hardware for the next space weather event, active monitoring ensures our technology remains secure. That brings us to the end of today's episode. Before you head off, here are a few ways to stay connected with everything happening above our heads. First, make sure to visit Flarient.com for real-time space weather data, live KP index monitoring, aurora forecasts, and interactive orbital dashboards. It's the best place to see live space conditions as they happen. Be sure to subscribe to the Daily Space Podcast by Flarient on your favorite podcast platform so you never miss an episode. You can also head over to flarient.com/podcast to browse our complete episode archive and detailed show notes. Don't forget to follow Flarient across social media for real-time alerts whenever solar activity spikes, and join the growing Flarient community of aurora chasers and space weather enthusiasts. Finally, download the Flarient app on your smartphone to get instant push notifications delivered straight to your device whenever geomagnetic storms strike. Thanks for listening. I'm Ollie, and I'll catch you again tomorrow for your daily space updates.